Welcome everyone to this data science seminar. I know a lot of you have had a very tough week and a very tough day as well, but I'm sure during the next 2.5 hours you'll get a lot of new knowledge and perhaps meet people who can help you with your own ideas about data, whether it's sensitive or medical. Today we have 5 wonderful speakers. The current idea is that because we have 5 speakers and only a limited amount of time before this Thursday goes, ends, then we'll have around 20 minutes per speaker to talk, 5 minutes to have questions from the audience. And then during our coffee break and our networking break at the very end, we can, everyone here can talk to our speakers perhaps one-on-one or maybe in a group. You can talk to each other then. But until then, we're not having today a panel discussion because, again, there are quite a lot of us speaking today. So any kind of questions during the presentations, be sure to write them up and ask right after the presentation. We'll have a 5-minute period for that. And if you don't have a question then, or you forget to ask it, then yes, those breaks will be the place where you can ask them. But without further ado, I'll give you our first speaker today, which is Raivo.
Great. Okay, hi. Everybody, my name is Raivo Kolde. I'm here Associate Professor of Health Informatics. And I'm going to tell you today about adopting common data model for Estonian health data. And when I speak about health data, so what do I mean in here, the Estonian health data? We have in Estonia health data in different places. So for example, we have these national electronic health records. So these are, like in English, maybe better called like either discharge report or progress notes. Basically, they are describing one episode of treatment for one patient. And as you can see in this example, they contain like some like structured information, like the diagnosis and procedures that were done, like the dates, but also there is lots of free text in there, or like semi-structured information within that free text that describes like the patient's symptoms and the history and so on. So this is one source of health information in Estonia. The other source is the health insurance claim from Estonian Health Insurance Fund. So to pay the doctors, the health insurance fund needs to know like what was done to the patients, what were the procedures, and also why these were done, like what were these diagnoses that these procedures were related to. And then we have also the digital prescription system that is used for almost all of the prescriptions in Estonia since 2010 already. So there is also a trove of information about like what are the drugs that the patients are prescribed and like when are the patients buying them out and if they are buying them out. And then there is also the medical imaging and hospital information systems, but like these are harder to access for research, and that's why we're not talking about them today. But like there are lots of interesting things that you can do with this data, but every time you look at any health data resource, you understand immediately that you cannot just take the data and start analyzing. There is lots of cleaning and processing that you have to do. For example, in US, there was just recently done a study where they were just like looking at the words in the medical records, and they found out that more than 50% of words in all the medical records are duplicates from previous medical records, meaning that you just cannot take like everything in and start analyzing. You have to do some like deduplication, for example, but lots of other things as well. And also, as I said, like much of the information that we have in Estonia is in the free text. And like if you want to extract this information, again, it needs quite complex pipelines. So I just put a picture here about some of these pipelines that we have in our group just to get the information out from the medical records. But like when you have done this processing, cleaning of the data, then becomes a question like, but where do we put this data? So we have to store it in some kind of a table, but what kind? So it seems like a simple question, but actually it's not, because like we have to put the data store the data somehow that it would be easier to do studies on it. So we can make like a study-specific data table, for example, that we want to use. But like then, if we do a next project, like we have to figure out again a new data table that we have to use, and like this becomes repetitive. So we would need like a more general data model. But to define a general data model and like say where all the different features are stored, how they are stored in there, how they are coded, this actually becomes a quite huge undertaking that requires like lots of experience. Unfortunately, we are not the only ones who've had this problem. So researchers in US already had this problem like 10 years ago, and they defined this OMOP common data model. So it's a patient-centric database structure. So you can see the tables in there. So what it means, it's patient-centric. It's because the main object there is a person. Each person has observation period, specimen information, death information, and information about the visits were like what, and there are the subtables that are telling you like what drugs were prescribed, what procedures were done to the patient, what were the diagnoses and measurements, and so on. So this is a pretty generic table. Generic tables in there, and like to our experience, most of the medical data that we have in Estonia can be put somewhere in these tables. And the nice thing about these tables is that like all the fields in the tables are very regulated. So you know exactly like what type of data goes in there and how it should be coded. So that there is also like these support tables about like vocabularies and domains and so on. So this is this database structure. It's extendable if you have some information that cannot be put in there. For example, genetic information, you can like extend it somehow. And it's built for analytics, so it's very easy to do analytics on top of this data. And it has a relational design, so it can run on like any SQL database engine that you like or prefer. So having this data is in this format is very good, and that's what we've been working on. And what this single format will allow you to do is actually to perform federated analysis. So here is a slide by the Eden project that is promoting the use of OMOP in Europe. So that's how they depict it. So let's say you have an analysis ID, you have some analysis code already, and then you have figured out also like link to one data set. So you want to plug it in, fine. But then you want to run exactly the same analysis on some other data source. And then it turns out that the link to the data doesn't work because the data in every different data source, like across Europe, in different hospitals, in different like regions, is different. And actually, like adapting your analysis to these different data sources is a huge pain because you don't even usually get access to these data sources because of the privacy reasons, and like you have to be really an expert on the data set to know how to program that. So practically, it becomes almost impossible to do like any complex analytics across the countries. But if you have all the data sets in OMOP data model, you know exactly where to find specific piece of information, you know how it's coded, then this problem goes away. And you don't even need to have the access to the data. You just send your code to the data owners, and then they send back the results. So, and you can then aggregate the results and publish them. And this makes everything much simpler, and it also gets rid of most of the privacy issues and like ethical issues that we might have in this analysis. And since we don't have to spend so much time on like just processing all the different types of data, it also leaves us much more time to work on this like the designing a study and like working also on the study methods. So I think one underappreciated aspect of this is that having this common data model also allows standardization of tools. And I have a very small example here, like why this is necessary. Whenever we are doing this analysis on any medical data, the first step that we have to do is always that we have to define the patients that we are going to study in our analysis. And here is a small cutout of the description found in a typical paper that describes the patient cohorts, as they are called. So, for example, there are conditions like patients have to be more than 17 years old. They might have like at least like 1 inpatient or 2 outpatient visits with diabetes, and so on and so on and so on. So the things can get pretty complex. And but now you have to also tell the computer like what does it actually mean to find these patients. So the doctor comes up with this type of description, but the data scientists have to turn it into a code, which might look something like this. So as you can see, there are like lot more words in the code than there are in the description of this cohorts. And this is actually a great source of ambiguity. There was recently just an experiment taking these exact descriptions and giving them to 9 teams of expert data scientists who do these things every day. And they had to encode the same cohorts on the same data set. And what was the result? All 9 teams, because they were expert data scientists, they were extremely confident that they got it right. But like all 9 teams got different results. So basically, that shows that even if you read a paper and everything seems fine, you cannot be really sure like what was actually done in the paper and like who were the patients that were actually studied. But in this case, the Odyssey consortium that is promoting the OMOP in all over the world, they have come up with this standardized tool to make these cohorts. So there is a nice web interface where you can put in all these different conditions that you want to have. And then it generates this machine-readable JSON file. So it's not very nice to read like when you're human, but like by making it machine-readable means that it's very transparent. So you can go back and like import it to the tool, and then you can see it like in a human-readable form. So it allows a lot of transparency between for the people. So instead of publishing this vague description of the cohort in a paper, you could actually put there also your JSON file with the cohort definition, and everybody understands exactly how this cohort was defined. And it also allows reproducibility, so you can run it on your own data again, but you can run it also on any other data set that is in the OMOP format. And it allows also to make more complex cohorts, because like sometimes people get a little bit leery. They don't want to include as many conditions in the cohort definition, because it's just like it gets very messy like in your method section. But like in here, you can make much more complex definitions in there. And at the same time, you can be sure that it's always calculated correctly, because like if the software has been used for many studies already, it probably has most of the stupid mistakes already ironed out. So this is like the power of standardization of tools. So with any type of analysis that you do, when you can do it in a standardized tool, you probably get better results, and you get all these bonuses with that. So this is the pitch for the OMOP data model. So what we have been doing in Estonia. So in Estonia, we have taken all these different data sources that I showed before, and like we first started to clean them and like process them individually, but in the end we have come up with this ETL process that we can put all this data together, link it up, and put it into the OMOP database. And this process can be run on like basically in Estonia you cannot get like all the data from all the sources and then do it. Like you have to write the ethics committee proposal, and then ethics committee approves your like study proposal. So you have to ask for the data any time. But now when we ask the data, we can just run this code and get this nicely formatted data table already. And then we can already get the benefit of having our data in there first by running these standardized tools for data quality checking, where most of the different or many different quality checks have been implemented already by others. So this is one way that we can benefit already by adopting this. but it also allows us to be integrated more into European research networks. So IMI Eden project is compiling a network of more than 100 data sources, and they are actually giving money to the different data sources that they will convert the data to OMOP. So now there are more than 100 of these, and they are start to run more and more studies in this. And then we are also part of the IMI Optima network of data sources that is more cancer-specific project where we will start asking more cancer-related questions on the data, and again, data from different countries. And I'm most excited about this last one, the European Medicines Agency Darwin project. So this is a data network for providing real-world evidence for regulatory decisions. So European Medicines Agency is the organization that has the power to tell that you can use this drug in Europe or not, or like, and then they have to make all these kinds of decisions, and they have made their goal that they will use more real-world data, like Estonian medical records, in their decision making. And this project is the first one that gathers up now a network of data sources where they can ask the questions and take this input to use in the regulatory decisions. And we hope that Estonian data will also contribute these in the near future. But another part is that, like, although there are like already great tools for analyzing data on OMOP, then there are lots of opportunities for just like encoding, making tools for already very common analysis that people are doing like in an ad hoc phase in the data set. So one of the projects that we have in the lab is just like providing tools for doing modeling disease trajectories using Markov chains. So these models are often used for economic assessment of health technologies, and like we are making a tool for that, and like it's already seeing like lots of interest in the regulatory bodies. But while creating these tools, we can also see that having this number of data sources that you can use and compile actually creates a lot of more opportunities for analysis that hasn't been performed before because it was just impossible. So it offers us also a way to reimagine how the analysis is done in real-world data, and there are like lots of interesting opportunities that we can take in that direction. So we have interesting times ahead, and like I'm not doing this work alone. So these are the people I'm working with. And if you're interested in more information about what we are doing, then we just made our webpage, healthinformatics.cs.ut.ee. So you're welcome to visit that. Thank you.
Okay, so we now have a bit of time for questions. If you have questions, please raise your hand, and I will give you the microphone so we can also get the sounds right.
Thank you. So in the ETL process slide, it was 9, I think. Yeah, this one. So you did the ETL and you linked the data sets before you converted them to OMOP. So
the linking is basically done like in the OMOP database. So like we have, in Estonia, we have the ID code for every person, so it's the same in all data sets. We don't have the ID code, we have the pseudonym, but like it's the same. So we just like put the data from each source like to these tables, and like then we have linked database. So
basically what you did was you did the ETL for all of the separate databases and then you linked them? Or did you link them before and
we
then
dump it all into the same database? There is just like one field in the table that says like what's the source of the data, so it claims our medical records.
What my question is mainly is that could then the original databases actually be in OMOP format, or that is that they would still need like, or could they like export data in OMOP format in the first place so you wouldn't have to put them into the OMOP format?
That would be ideal if all of this would be done like on national level. So like I don't know, the Ministry of Health basically would compile this type of database already, so we could all access this with standard tools. So like it would make the analysis for everybody much simpler. But like right now we are like kind of spearheading this thing in Estonia, so like we have to sell it to them still.
Okay, thanks.
Yeah.
So, do you have access to primary data as well, or it is just secondary data that is research data? Do you have access to clinical data?
What do you mean by primary data?
So there are two types of health data. There is the primary use, that is the clinical data for alive patients. I mean, patients.
So most of the patients are still alive, fortunately. But like, yeah.
There are some other sensitive data that is not for people who passed away, but the patients, I mean, alive patients, not the person is alive, but they are under treatment. So if you do some analysis for this data, you are, for example, you are sequencing a tumor or doing variant calling for a sequenced cell for a cancer patient who is already under treatment. This is the clinical data.
So there is certainly a delay in getting the data because like the national medical records, they are submitted after the episode. So like it might be that the treatment was done in July, but they submit a document in like December, and then it also takes time when we get the data because we don't get it all the time. So like we don't get it like live in terms of like yesterday patient went to the doctors and like tomorrow we will have the data. So there is a considerable delay in there.
Yeah, I understand that, but the clinical data normally requires additional ethical approvals than just the secondary use research data.
Yes.
So do you have this in place? Because
yes,
this is not trivial in many countries.
Yeah, well, so first our process is that like we first have to apply for ethical approval for our study, and then we get the data. But like we figured that the easiest way to do things is still that then we take this data and convert it to the OMOP format using our process that we have already. So, yeah.
Yeah.
But we have like many different data sets. We don't have like one data set that we can use. That would be perfect, but unfortunately we don't.
Thank you. Did we have a question at the back? Yep.
So my question is like about linking the data from different data sources. Did you consider any linked data or standards of the semantic web technologies, like or the RDF data graph for connecting the data? Maybe it's first name here and it's if name there for the same things for linking data from different data sets.
In Estonia, we have this luxury that we have the ID code that is very simple. It's very simple to link. You don't have to do any complex linking.
So it's like, you know, the unified identifier. Okay,
Yes.
thank you.
Yes, yes.
What is the situation in European countries right now? Is OMOP form something that has been agreed on as a common standard, that everybody tries to convert their national databases into this form, or are there other competing forms, or is there any agreement yet?
I don't, like for research data, I don't know any as popular competing formats. Like there are like, for different purposes, there are like different, like OpenEHR is like something that is like kind of similar, but it's more meant for the operational use of things. But like OMOP is specifically geared towards the secondary research, like use case. And I think this like EMA Darwin project is one of like the, how to say, I don't know what was the original term, but like kind of like trailblazers or something for the European health data space. So they are trying out in practice many of the things that they want to achieve with the European health data set, data space law afterwards. So in all likelihood, the European health data space that kind of should make the data available across medical data available across Europe will look much like the Darwin project, where you have like national nodes that have the data in the same format, and you can like send your analysis code to these nodes and run it and like then compile the results.
If I may, an additional question. What is your prediction? When will the European Common Data Space actually turn into reality?
I think like technically we are working towards that, but like in terms of like legal issues, I have no clue.
Okay, we have time for one more question. Yes, 1 second.
What are you doing with foreigners without ID?
I think foreigners have the IDs. Like if you have the permission to live in Estonia, you have the ID number. Yes. Yeah, yeah. Tourists, yeah. Yeah. I guess it's like much like Denmark. Like I don't know the situation elsewhere, but like I lived for 5 months in Denmark, and I was forced to get an ID in there as well, like some number. So.
But thank you, and it's time for Liina.
Yeah. Thank you.
Can I have the pointer? Thank you. Hi, I'm Liina Kamm. I'm a senior researcher in Cybernetica, and the logo has turned blue for some reason. Cool. I wanted to talk about whether privacy versus usability in data is a zero-sum game, or whether there's something to win there or not. So is usable privacy-preserving data analysis an oxymoron? Oh, the colors. Oh, great. So when we talk about processing personal data, we think about two ways of processing personal data. So one of them is that, let's say we have this person, Wiley. She's a tall woman. She's 27 years old, and she has high blood pressure. And she goes to the doctor, and she gets a prescription. In Estonia, she will get it a digital prescription, so it won't be on paper, it will be digitally. But the doctor has to know who Wiley is, right? It's not like I anonymously go to a doctor and then the doctor just gives me a prescription. So the doctor knows who Wiley is. Then Wiley goes to the pharmacist. The pharmacist also needs to identify her to actually sell her the medicine. And then she gets the medicine. Now, this is not the part that we're talking about here, because here a person needs to be identified. However, when we talk about analyzing the data afterwards, because we can get information from this. We can get information from the doctor's visit. We can get information from the fact that she bought her prescription, or how many times she bought her prescription. What else did she buy in the, like, what other prescriptions did she buy, and so on. We can get information from this, and based on this information, we could make decisions, and based on these decisions, we could maybe improve health, maybe preempt some conditions, maybe do some other things. So we can actually use this information to the person's advantage. But this analysis, however, does not need to be done in an identified way. So here we don't actually need to know that it was Wiley who bought the prescription. We don't need to know that it was Wiley who was told. We don't need to know anything about her. We just need the information, right? So, and to do the analysis. So what I'm talking about here today is this part. So it's the part where an analyst analyzes the data. So when we're processing data, and when we're processing, especially when we're processing sensitive data, then it is very important to start with an inventory of your processes, of your data sets. So you have to ask the following questions. You have to ask, what kind of data do I have? Where are the data kept? What do I want to do with the data? Where will they move in the process? Who is going to see them? And this will help you figure out what kind of privacy-preserving technologies you will need to use, what kind of measures you will need to take to preserve the privacy of the individual. So, and what we're going to get to is the fact that not every privacy-preserving technology is actually suitable for every problem, and but some are more suitable for some problems, others for other problems. It doesn't make sense to use like the most most complex and most privacy-preserving solution when you actually have consent from people. So there is a privacy complexity trade-off where we say that you know probably the privacy security trade-off, which is that if you switch off your computer, then it's very secure. Right. So it's the same with privacy and complexity, probably. That if you want, you can use pseudonymized data, or actually, sorry, this one. You can use pseudonymized data, or actually like use data with ID codes. Or then you could not use data at all, which is on this side. But we will not look at the corner cases because it doesn't really, you never need the ID code. You can always get by with a pseudonym. And you really want to use the data because you want to get information out of the data. So we will stay with we will kind of cut our borders and go from pseudonymized to encrypted or secret shared data. And the problem is that the privacy risk is high with the pseudonymized data and low with the encrypted or secret shared data. The colors are really random because they were red and green. So, you know, it's a bit like whatever right here. Okay, so like if you look at it, then using pseudonymized data is easier because it's basically like a cross table. Everyone has seen pseudonymized data. What they do is they simply take off the ID code and basically you have your data. You might do a little bit like grouping or do a little bit of the you add some anonymization techniques, but basically you're just working with a cross table, which we learned to analyze in school, like already in the high schools or maybe later in university. However, if we go to the encrypted or secret shared data, then that is very complex. It is complex to use, it is complex to set up, it is complex to organize, so everything about it is complex. And the frequency of use, of course, is also, so if it's easier, it's more commonly used, if it's complicated, it's more rarely used. However, the problem here is that we can't actually put usability on this same kind of line. And okay, this works if we're talking about pseudonymized data and encrypted or secret shared data, which are the extremes in this figure. But if we want to put all of the privacy-preserving technologies on this graph, then we can't do it in this kind of one-dimensional space. So I've done it in 2 dimensions. However, there is actually like a 3rd dimension as well, which will be usability, because if you use some of these methods, then you're losing some of the utility of the data, meaning that you will lose some of the people in the data set, you might lose corner cases, you might lose important data, you might not get the results that you wanted. However, so here you can see that pseudonymization, while it's the easiest to use, it has high privacy risk, and secure multi-party computation, while it is very privacy-preserving, it is complicated to use. However, if you look here, then we have, for instance, synthetic data, which is very easy to use once you've generated it, and it has low privacy risk because it's basically random data, right? However, what is missing from this graph is the usability axis. And because we don't actually know how usable synthetic data can be. It can be very usable. On the other hand, it could be not so usable. And it's a very case-by-case basis thing. So, pseudonymization. I'm going to go over a few of the techniques that were in the graph. Pseudonymization is, as per GDPR, is when you basically take away the direct ID codes and you leave all of the rest of the data. And what is good about pseudonymization, that even though it breaches privacy a lot, it is the results are linkable back, or the pseudonymized person is linkable back to the original person. So for instance, if we're trying to carry out personalized medicine, then if we do a study and we find out that there's something wrong with these specific people, we can send it back to the doctor, and the doctor can then tell these people that they need to do more analyses or so on. So you can link it back to the original person. Pseudonymization basically works in a way that we have a table and we take away the identifiers.
let's say here we take away the ID code and the name, and that's it. You can take away more. You can employ some of the anonymization techniques, as I mentioned, but this is the simplest version. Anonymization, on the other hand, is in GDPR. Basically, GDPR says that if you anonymize your data, then this data set will no longer adhere to or is no longer governed by the GDPR. So basically, you don't need to look at GDPR if you have an anonymous data set. However, it does not very strictly define what an anonymized data set is, and here is a standard explanation of what it is. And this says that the data is irreversibly altered so that the data subject can no longer be identified directly or indirectly, even by the data controller. So even if you encrypt your data, and if you still have the key, it is still possible to revert it. It is not anonymization. So, anonymization can only be analyzed on a case-by-case basis, which means that you really don't know whether you anonymize a data set, you don't know whether it's going to be anonymous or not. Because there are machine learning methods that could find a person in the data set, in your anonymized data set, could infer like this, that this one person is there. And if you can find one person in the data set, it is no longer anonymous. And then instantly it becomes, it should adhere to GDPR. So you're kind of stuck there because you won't know until someone breaks your anonymization. You won't know whether you have to use GDPR or you don't. So the anonymization process, it doesn't work by just removing the IDs. The anonymization process defines something like quasi-identifiers, which is a set of identifiers that identifies you uniquely in a data set. And the problem is that finding these quasi-identifiers is really difficult because you never know which combination of attributes will identify a person in the data set. And you could go through all the combinations, but that will take a lot of time. So, for instance, if you take people who graduated from university in a certain year, let's say women, then sure, they won't identify anyone. Now, if you take that they graduated PhD and from computer science, then probably that will identify you. But if you take these separately, then like graduating PhD at a certain year doesn't identify you. So how do you name these things that will make up the quasi-identifiers? And the process is final and should not be able to be reversed. So if you're doing analysis and you find a certain marker that you should inform people about, then you can only inform the doctors about this marker, and the doctors should then see whether a person, somehow find out whether a person has this marker or not. So it's a bit difficult that way. And as I said, then you can only understand whether a certain set or certain data item is anonymous is only by case-by-case basis, and you might not find it when you're dealing with larger data sets. So here are several examples of anonymization. Let's take our Valli again, who is tall, and if we take away just the name and the ID, then Valli will be left out because she's the only tall person with high blood pressure in that data set. Then let's leave out something. What makes Valli unique here is her height. Let's leave out the height. And let's leave out her age. But now the problem is that we actually want to have her information. We want to analyze her information because she is the tall person with high blood pressure. She's unique in some way. We actually need to need her information here somehow. So she gets lost in this data set. So what we should somehow keep her age. How do we keep her age? Okay, let's compute the body mass index. But here, now we're computing the body mass index. But what we're and she gets into the database because she has the same body mass index as Mari did, so she gets into the data set. However, now the problem is that she has the same body mass index as Mari does, and Mari was short, or well, like normal height. She was 165 centimeters, whereas Valli was 194 centimeters, and their body mass indexes are exactly the same. So, of course, this is a doctored data set, so that they would match, but still, I mean, it could happen. It could happen that there are two people who have the same body mass index in the data set, and here we also lose her age, her height, even though we're using her height in an aggregated manner in this computation. So we're losing data. So the usability is the question. And what's important to understand that pseudonymized data are not anonymized data. So if we're talking about this is an anonymous data set and only the IDs have been removed and the pseudonym has been given, that is not an anonymized data set. This is pseudonymized. Because in pseudonymization there exists a link back, in anonymization there does not exist a link back. And the only thing that I do want to mention is that in common language, anonymous also describes cases where the identities of individuals are only hidden. And this means that if we're talking about an anonymous source who provided information, or we have these pealtnägija clips where the eyes are hidden, then that is anonymous in common language. It's not anonymous as per GDPR because someone there still knows who that person was. The person whose source it was knows that person. There is a person who can link it back to the original person, and probably the people in the studio know who the person was with the thing above their eyes. Okay. Yay. So also another thing that already Raivo talked a little bit about, we can employ federated statistics and federated learning, where we don't actually send any of the data to a central party, but we do our analysis beforehand, and we send the analysis result, and those will be combined. Now here the problem is that sometimes if you send your machine learning model, then some of the information can be inferred from there. There are also machine learning methods exist to find people in the machine learning model. But however, you could somehow hide the model before you combine it, somehow encrypt it, and then use homomorphic encryption to combine it in that way. So that would actually solve that problem a bit. And also you would have to have an algorithm or a model that actually can be combined from two models. So if I would send, let's say in statistics, if I would send average to the center and the other person or the other hospital would send average, then the average of two averages is not the average of the two data sets. But if I revealed a little bit more information, if I were to send, let's say, the count and the sum, then the sums could be summed, and the count could be divided by the sum of the counts, and then you would get the average of the two data sets. So I would reveal a little bit more information, but not my whole data set, which is, I think, a bit better. So I would say that it's not like a zero-sum game. So it's not like very difficult to use. It does maybe give us more information than we would get if we were using like encrypted computation, but here it's still a little bit better than sending the whole data set. So data synthesis is a process where a model is trained based on your data set, and then data are generated based on this model. So this is the part where I was talking about. This is not real data, or these are not real data. This table, random data, only it's generated based on other data, and it should actually retain the relationships and the distributions of the original data set. And, I don't have the example. There is a very good example on the web page, thispersondoesnotexist.com, which is .org, something. This person does not exist. You can look it up in Google. And where they used generative adversarial networks to generate images of people. And they look like real people, but they're not real people. So this leads me to believe that it is possible also to retain the relationships in tabular data. And you can do machine learning, you can perform machine learning on it. However, the problem is that if you're too precise, then you might leak more information. So it's, again, like you're on the balance there. Then we have trusted execution environments where you're basically doing computation on encrypted data. It's a place in your computer's processor, an enclave, where what you basically do is you input you encrypt your data, you store it on the drive in encrypted form, and you send the key to the enclave. And then the computation is performed here, the data is sent here, opened here, and then computed. The results are encrypted set here, and the output party can then query them from here and get the key from this enclave. And you can also audit this process to see that the enclave is doing what it says it's doing or promises to do. Okay, so we also have secure multi-party computation, which is my area of expertise, where we basically distribute every value we distribute between 3 parties, and we distribute it in a manner that we basically additively break it up. So it's 3, 17, and 7 is what 27 becomes, and this, if you add it together, you will get 27. Now, and here it's basically random values, and only if you put them together you get the actual value. And you can use algorithms or protocols to actually compute on these data. Now I'm getting to the part where I'm going to talk about whether secure multi-party computation is actually is machine learning feasible in secure multi-party computation. And the good thing about secure multi-party computation is that you keep all of the IDs, so not the IDs, but let's say pseudonyms. So you can link databases there, which is a very good thing, because you can't actually link databases in federated learning. You can, federated learning is done on horizontally partitioned data sets, so you have basically the same data in both data sets. But if you have vertically partitioned data set, like age here and, I don't know, gender and salary somewhere else, then you can't, using federated federated learning, you can't put them together afterwards. So you have to link first and then do the analysis. If you have the data sets of 2 biobanks from different countries, then you can put those together because they're in the same model. Here you can link databases. It has sufficient privacy protection measures because you can't see individual values, not even the system administrator can see them, and it preserves the privacy of the individuals. It does have a high computational overhead, but the administrative overhead could be a lot. Because we've tried this out. Basically, we have a tool called German MPC. It has side channel safe algorithms for linear regression and from linear regression to XGBoost. We have an R-like interface so that the data analyst or data scientist doesn't actually need to know how secure multi-party computation works. You can just use it. It looks like R. It has kind of a manageable overhead, except for XGBoost, which on large data sets, which does not yet work very well. We're optimizing it. Lasso logistic regression shows promise. We've also demonstrated it for neural network evaluation. However, it's not feasible for training neural networks, which we hope we can do in a federated manner. We had a project where we used ShareMind MPC to do machine learning, and I think it was the same project where the OMOP data sets were also used. We wanted to predict the hospitalization of chronically ill patients, and so that if more frequent checkups were done on these patients, then it could reduce the number of hospitalizations. And we had the medical data of 130,000 individuals and up to 25 million entries in one table. What we did was we did basically the same thing that was done in the open or with data that wasn't secret shared. We selected people with chronic illnesses, everyone except cancer diagnosed people. Then we linked and cleaned the data, and the output was a single table with around 150,000 rows and 500 columns. And then we normalized the data, split it into test and training sets, and we trained logistic regression and lasso logistic regression on the data. And now the benchmarks. So for training, we tried different algorithms, but then and what we did was we experimented with floating point and fixed point numbers, which actually, this is my last slide, which is because if you use fixed point numbers, then you lose some of the precision in computations. However, in machine learning, it's sometimes okay. And the pre-processing took 80 hours, which is a lot. But if we had the OMOP version, then it wouldn't have taken that long, because we did everything we did all of the linking, all of the data cleaning, everything in secret shared format, because we wanted to see how long it took. If it had already been in OMOP format before, then it would have been considerably faster than 80 hours. And last logistic regression took 22 hours on this data set. And we got quite good precision. So we got, our logistic regression was a little bit better than the one without the secret shared one, but this is because of different reasons. But it was worse than the XGBoost one. But we did not manage to complete our our XGBoost also completed, but it took way too much time to be usable in practice. So what I'm trying to say is that even though it is a bit slower, then waiting for a year for data could be even slower. So you just take the 80 hours, you see whether you can use the data or not, because we did another study where we actually waited for a year for data, and then we found out that it's actually not feasible to do any kind of machine learning on these data. If we had done this, it would have been privacy preserving, we would have found out sooner, and then we wouldn't have had to wait for the data for a year. Thank you.
Okay, thank you. We now have time for some questions. Please, none of them about why the colors are wrong. I don't know, I'm sorry, but I'll find out. Okay. Yeah.
Thank you, Liina, very much for this presentation. So in a way, you are saying that using discrete data, tabular form, if if you take all attributes by attributes, cross-tab or cross-hypercube, if any cell has one single value, one person having this combination, this data is not anonymous anymore. Taking two values identifies one row uniquely, not anonymous.
If you can link it back to the original people, then yes, that's not anonymous.
Okay, that is a big assumption, because my kind of follow-up would have been that if this is a random sample of, we take 10% of random people from Estonia, so you don't know if there is this 194 centimeter tall woman is unique in Estonia or not, right?
Yes, but if it's a sample from a data set where it was originally, where she was originally, you can link it back to the original data set, then it is still, if she's unique there.
So but that assumes that you have access to that complete data, which you probably don't.
Yes, but someone does.
Not legally.
No, but I mean the data controller, the original owner of the data, they do. And if they can already link the data that they've given you back to the original data set, then that is not anonymous. It's whoever. I encrypt data for you, and you work on the data, and I don't have any reason to give you my key. It's still not anonymous.
Okay, but okay, that other data source is either illegal or illegally linked to that.
No, I mean, you have, where are you taking your sample from? You're taking it from some hospital, let's say. The hospital takes a sample.
Health insurance fund.
Okay, let's say the health insurance fund. So they take a sample, and if they can link it back to the original data set, then it's not anonymous.
Yeah, but by definition, they anyway have that access. They have that.
Yes, but the problem, the point of anonymization is that you always find you. So if you use, for instance, anonymity, then there's always like.
So pseudonymization is still, well, this is pseudonymized.
Yes.
Yeah.
Yes.
Okay.
If you can link back, then it's pseudonymized. There are people back there.
I have a question about your product. Does it handle versionized data? For example, when it happens that people's ID codes change, like they are from one year to other, second year are with one ID code, later they are with the other one. I have to handle this, or is this something I have to take care before I start this analysis with your this Sherman thing?
So we can basically do any kind of thing you can do in the open, you just can't see individual values. So if you have a substitution of this is now, I know what the code was before, I know what it is now, then you can substitute it. You do it obliviously, It is that the database is shuffled. You do it like it's linked with someone. You don't know who it's linked with, and the database is shuffled again, so you don't know which record it was linked with, but you will know that it's now the new code. So let's say that you use pseudonyms, and then you want to change the pseudonyms to something else to link to another database. Then you can take the substitution table, you could put it in obliviously so that you can't see it, but the computer will, or the machines will do it for you. And so yes, basically the answer is yes.
Thank you. A question about the difference in the model fit. I mean, you said that there were various reasons for that. Question is, I mean, essentially running the same type of model on the same data, given the type of method, I understand there could be differences, but what was the reason? I mean, did you diagnose that as well? Was it because of Sherman?
So the reason, thank you for the question, because I didn't have time to talk about it, but there are several reasons. So one of the reasons is that since we did our training and test sets were probably different. And it's not that big of a difference. It's really like they're quite close. So one thing could be that it was the choice of the test and training data sets. Another reason is that in secure multi-party computation, because we want to be side channel safe, we can't actually check how, we can't check our how many iterations we make. We can't check based on the data results. So we say that you will now do 10 iterations, and that's it. You will do 10 iterations when you need it, and if you reach your point of like no iterations anymore, then you will still keep doing the iterations, because we don't want you to don't want to show that okay, this algorithm finished in 7 iterations, because that leaks information. So we always do 10. It's just that if we wanted to finish in 7, then we would just multiply all of the rest by 0, and that basically zeros to the result. But you won't know that because it will still compute the same amount of time. So it won't be faster if you finish in 7 iterations. However, we are less likely to overfit because we stop at a certain point. So we don't go further. So it could be because of this. Because I think our data scientists did try more iterations, and then it started to get worse results. So it was like, I think it was, it was probably a combination of the training and test set, and then that because we had to stop at a fixed number of iterations.
Okay, thank you.
That was another question. Okay.
One more question.
Okay.
It's a simple one, so it will not take time. So my question is like, is your solution only supporting tabular relational databases, or it could support other data models?
What other data models?
Yeah.
Do you mean?
Like, I mean, for example, if the data already in textual format or, graph format or whatever.
Okay, so we do support the graphs, but we do support text as well. However, text, we haven't tried any kind of text analysis in ShareMind, because that's going to be very costly. So it's a very complex problem. It takes time in real life, so it will take like exponentially more in the secret shared format.
If I may ask, like what kind of graphs that you are working on?
We've worked on they're basically, currently what we've worked on is trees, because we have a client who has who is interested in the electricity electricity framework graph, basically. And that is, it is luckily a tree, so they don't have cycles in them. So
okay, thank you. Thank you very much.
Yeah.
Very much again. And we have time for a coffee break, so we can all give a quick stretch, and we'll be back here by 15 minutes. Okay, so welcome back, everyone. We're only 10 minutes behind schedule, so I think we can still make it before tomorrow comes. But without further ado, intro. Here we go.
Yes, hello. My name is Abdulrahman Azab. I work at the University of Oslo as a chief engineer. I'm also a senior advisor at the Nordic Infrastructure Collaboration. My background is HPC, sensitive data, cloud computing, grid computing. I'm part of the Lumi user support team. How many of you know about Lumi? Okay, very good, very good, yes. So today I will talk about the Federation of Cross-Border Sensitive Data Analysis and Processing. So the previous talk I enjoyed very much. It was very good about how to do the actual analysis. And the first talk was about processing patient data, but I think it was all in Estonia, but from different places. So now we talk about cross-border. Cross-border, it means data located in different countries. They have different legislation. People, when the GDPR came, they were thinking, the GDPR, everyone has to be monitored, and there is a you know what was the most famous thing about GDPR? Why it was a big noise? You know why? Because of the fines. The fines are severe. You have to pay a lot, millions of euros, if you get caught. But actually, it turns out that the GDPR was not the most horrible thing in terms of legislation. Actually, the local legislation are even more strict than GDPR. In some countries, I don't know about Estonia. In Norway, for example, they care much about consent. In Denmark, you cannot take the data outside Denmark. It seems that you are lucky here. I mean, you are not that strict. I don't say that you are not secure, but sometimes it's a bit too strict. So for cross-border cases, what is the meaning of a cross-border case? A cross-border case is there is a researcher here in Estonia. There is some Estonian data stored maybe in the data cage here at ITAIAS. And this researcher have a collaborator in Norway, and there is Norwegian data stored in TSD, the Service for Sensitive Data that we have. And those are, they are collaborating together. And each one of them needs to get access to the data in the other side. It's not trivial. In Denmark, if you want to do this, they have to do a trick. They have to give you access through being registered as a guest researcher at a Danish university, which is a member of the group of universities that are recognized by Statistics Denmark. Not all the Danish universities are recognized by Statistics Denmark. So you get a guest researcher position there to be affiliated with the Danish university in order to be able to get an account and get access to that data in Denmark. You are not doing any research there. You don't need that just to get access to this data set. Something that you may need only for a few hours or a day or a week. And you have to get a position and an email for this. So things are not very trivial. So the title of my talk is Towards Federation of Cross-Border Sensitive Data Access and Processing. We heard about the European Health Data Space. The European Health Data Space is mainly about federated access. When we talk about federated access and federated compute, there is a difference between those two. Federation, it means that you are in some place and some of the things that you need to get, they are happening in other places and you are not aware where these things are happening. Federated access, it means that with your Estonian ID or whatever the AAI or IDP that you have, you can get access to some Norwegian data, some Danish data in Denmark. This is federated access. Federated compute, you just need to do some analysis on some data set, and this data set can be located in different places. You have the portal here, the user, the GUI here, and the object store is in one country and the compute is in another country. Maybe the data is in Denmark and you want to compute on Lumi and you have the portal in Estonia. This is federated compute. So in NAIC, Nordic Infrastructure Collaboration, we have had some projects throughout 8 years now. Started with Trigva 1, and Trygve too, and now HILSA project. Stefan here is a member of the HILSA project. We'll talk to you about the federated EGA and maybe other stuff. So we worked on different work packages or different deliverables. One is processing platforms, cross-border processing platforms and cross-border workflows. AAI, ELSI, ethical, legal, and social implications, and sensitive data archiving, and cross-border use cases. And again, cross-border use cases are not just health data use cases, there are cross-border health data use cases. In the Nordics, and maybe I would say the Nordics and the Baltics, we have unique digital health registries, biobank, and other data collections. We are unique in that we are similar in many things, and that we are more strict than others in many things. Some other countries, they are a bit more strict in certain things. In Germany, they are too strict in certain things. Yes. In France, they are a bit too strict in certain things. In Germany, for example, they have the federation. Claudia can tell you more about that, of course. So we have these services in the Nordics. Those are approved or trusted sensitive data infrastructures. And if I would use the GDPR terminology, they are sensitive data or data processors. The data processor is the one that you give the data, you analyze, and it keeps your data for the time of analysis, and then you take your data away. So this is TSD, Services for Sensitive Data at the University of Oslo, Computer Room, the life science HPC infrastructure at the Technical University in Denmark, Bianca, the University of Uppsala in Sweden, and sensitive data services at CSC in Finland. Some of them are platform as a service and software as a service, and one of them, the sensitive data services in Finland, is infrastructure as a service, IaaS. Regarding what we have done in ethical, legal, and social implications barrier, we collected some of the use cases. The scientists come to us, they come to us with the problem that most of the cases it's an access problem. You know, the technical issues are always the easiest ones to solve. I think I heard this in your talk. So the easiest ones to solve are the technical ones, but the most difficult ones are the legal ones. Lawyers are always standing in the path. If you give it to engineers, they can do anything. But put lawyers, they can stop anything. So some of the barriers were consents. How to get consent. For example, in TSD, we are forced, because Norway is the most strict for consent. We have been asked to make a web portal. So the patient gives the consent for processing the data, fine. And the data is there in TSD. Then the researcher have the access rights to do the analysis of the data. We have been told that according to GDPR, the patient have the right to withdraw the consent, the right to be forgotten at any time. He can wake up sometime in late night, 12 o'clock, and feel like, I want to revoke the consent now. So the patient can log in to TSD through a portal and revoke the consent. Then the researcher, if he wants to do some analysis tomorrow, cannot do this analysis. Has to check then can log into an internal portal and see that the patient last night revoked the consent. It's not that hard in other countries, but in Norway it is like that. To determine who is the data controller, it's not trivial, because again with the GDPR terminology, the patient is not the data controller. The patient is not the data owner. The patient is the data subject. There is a data owner and a data controller. The data controller is not always clear. Is it the university? Is it the research group? So it's not very clear in all cases. Uncertainties regarding the legal basis for data processing. The patient give a consent for you to do this type of analysis on the data. Can you do another type of analysis on the same data, or you need to make another consent for the patient? It can seem to some of us, oh, don't be like that. You give a consent, that is fine. No, in some countries, it's not like this. You have to make another consent form, and the patient needs to sign it again. Data processor contracts with sub-processors. If there is a HPC facility at the University of Oslo authorized to do some data analysis, and there is some GPU needed that they don't have in this specific infrastructure, and they need to push it to some other place, they need to have a contract with that sub-processor. And then the data controller need to have the contract with that sub-processor to do the analysis. Influence of local non-GDPR legislation, which, as I said, in Denmark, it's much more strict than GDPR. Terms for processing and moving registered data, e.g. from Denmark. I just told you about the hell that we had in Denmark. So we produced some document we called it the Trygve Code of Conduct for having a Nordic best practices for LC issues for sensitive data. We made this workshop in Helsinki 2019 to do education for our engineers. There were some lawyers from different countries there, and we're planning to repeat this, of course. And we produced this LC checklist. So when we get requests for use cases, we ask them to fill in the form. And this form includes a lot of information based on our experience on what is needed. Because you need to resolve legal obstacles between two legislation authorities that are different. You have to match between the Danish law and the Norwegian law, and sometimes it's not only two countries, sometimes it is 4 countries. We had some use cases where 4 countries were involved. So this is our workflow for accepting use cases. We had to put a lot of stages in order to find if they are relevant, if they are possible, and the steering group of the project need to approve in all of these steps. So this was for the legislation part. Now for the federated access. This slide I presented in the sensitive data workshop in Tallinn this week. So now this will go a bit technical. How many of you heard about X509 certificates? Okay. How many of you heard about tokens? Oh, okay. Yes, some didn't hear about each either. How many of you have passports? Okay, very good. So what is the passport? The passport is a way of identification, international identification of you. And then this passport has visas. If you visit these countries where you need visa, the visa you get from that country, and then you have entry to this place for a specific amount of time. And when your visa is expired, then you cannot enter. You need to apply for another visa. So there are some ways of electronic identification. One of them is X509 certificates, and you get them from something called certificate authority, and it is valid for a specific amount of time. What is it? It's a text file. It's a hashed text file that includes information about who you are and what you can do. Tokens is another way, but it's a bit more flexible than X509 certificates because in principle anyone can generate tokens, can generate access token or invitation token for you to be a member of a certain group with a specific specific privileges. So if we have two e-infrastructures, two data processors, one in Norway and one in Sweden. So this is the case that we have in hand here. So if a Swedish researcher wants to get access to a Norwegian resource, if you want to get access for the first time, then you need to, based on the level of assurance, they need to identify you. For some data processors, it is enough to have your name and your email and address. And for some data processors, they need a copy of your passport. And for some others, you need to come in person with your actual passport. You cannot send them a copy of the passport. And some even, they need your fingerprint. So level of assurance is different. For you to log into that Norwegian resource just to access a data set because your collaborator is in Norway and you need to access this Norwegian data just to look at this specific data set or to do this small analysis, maybe for 1 hour, currently you need to go and manually register as a user, like the procedure that I mentioned about Denmark. For every single scientist, you need to do that. If we manage to have exchange of these electronic identification so that you register only once in one country, in one place, and then if you want to access the data in another country, you take a token that includes your electronic identification. Okay, how can I use that? Yeah, yes, that's nice. And take it to the other side, but the other side has to trust the tokens generated by the first site. And then, instead of registration, manual registration, you can have a temporary registration using this Norwegian token, and you register in the other site. And with this token, you can get another token that is, oops, what did I do? Another token, this small one, that is a local one, to access the actual resource, the secure server where the data is. You do your analysis, you get the results, etc., and you can even take it back if they are non-sensitive results to the original site. If we manage to do this, we are in the process of doing this now. If we manage to do this, then each Nordic user of these infrastructures can register only once and can get access to the other infrastructures. So we have the token implemented JWT in Norway, in production, in Finland, I think they have it in production. In Denmark, they are on the way. In Sweden, they are on the way. And the installation of this is not very complex. It is complex, but it can be done. So this is a very simple diagram of what are the actual components you need. So if you have a sensitive data infrastructure, if you want to do this for the Estonian data cage, for example, this is what you need in order to enable tokens, access via tokens. And tokens are not only for human access, but also for code access. And this is what is important for federated machine learning, for example, because federated machine learning is a code that moves and accesses some different places and get the neural network to be trained here with this data and change the weight, and then be trained there with this data to change the weight and be trained in a third place. And then it is well trained with the proper weights, and then now you can give some input data and give you the proper classification based on the supervised learning. Then federated compute. So this is another way of federation. These layers are taken from the grid-based model, or the WLCG. I don't know how many of you heard about WLCG for high energy physics in your CERN, you heard about CERN, yes. So this was the CERN layers, and oops, what did I? And this is another model that is the Elixir functional architecture for the compute platform. They define some standards, and those are the GA for GH standards. WES, this is the Workflow Execution Service, TES, Task Execution Service, and TRS, Tool Repository Service. And those are standard set of APIs. If you implement those, then you are GA4GH compliant. In the GA4GH, they have something called GA4GH Passport. We talked just about passport. So what is the GA4GH Passport? It's a format of a token that defines who you are, and this passport has a connection to other tokens, and these tokens are called visas. So if you want to access a specific sensitive data set, you have a visa for that, and this visa has an expiration period. How much time you have to access this data, and when this visa is expired, then you need to apply for another visa. And for each data set, there is a data access committee. Maybe Stefan will tell more about that.
I'm sorry, we're starting to run out of time. We have only a few minutes left.
How many minutes I have?
Actually, we're over already.
Okay, then I will go just to this slide. So this is the federation model for compute. So these red parts here are firewalls. So those are sensitive data processors. With this federation model that we are trying to build is to have a connection so that different users can use the same tools. By the way, for the tools that use for example, for cancer genomics, if you have an upgrade of the same tools, it can give you different results. So even when you do an upgrade, you need to do either the computations from the beginning, or sometimes we get requests, we need this specific version of that tool to process the data of this patient. So they need downgrade. So it's important to have the same tools for different data processor to do the actual processing. And to have a layer of data management, there are distributed storage solutions. I will not show them because there is no time. There is iRods, and there is Dcache. If you heard about them, you can Google them. Those are distributed storage solutions that provide encrypted data transfer, and also with POSIX interface. And then the aim is to have the application layer for the doctors, for the patients, for even the sequencers and the specific devices that are generating data, to go to brokers, and these brokers can direct them to the actual data processor, whether they are storage places, archiving places, or HPC places. Yeah, so I can stop here properly. And
yeah, thank you very much. I'm sure we can continue the discussion later on during the networking phase, but maybe one or two quick questions, if someone has so far.
2 minutes, yes.
Anyone, quickly? Okay, I guess then we'll thank you very much. And our next speaker is Taavi.
Panin sisse, kas on kuulda kuskil? Vist kuuleb. Nii, tere. Oh, sorry, I switched to English. Hi, I'm Taavi. So, first time using this pointer. Working. Oh, back a bit. Top button is the magic one, and that's the next slide. Okay, so I'm Estonian by background, but I've spent most of my life in the UK. And basically, I've come back to Estonia formally this January. So it's nice to be back in my homeland. And by background, just a straightforward doctor with an interest in public health. So actually today what I think I'll talk about is stuff more from my perspective, just hardcore health issues. It will be technically very amateur and dull and boring, so I'm sorry that I won't be able to inspire with the technical gizmos, but maybe just as a use case of what I'm interested in from a health angle will maybe be of interest to think about how these technical aspects can be applied for use cases like this in the future. So just a quick whistle-stop tour, 15 minutes about each of these, even though each one could be given a whole day, is why should we predict who will have a heart attack? What do we know about some of those specific predictors called socioeconomic states when they predict heart disease? How are these things implemented in the real world in different countries? What's sort of the research vision for me personally and the research group I'm trying to start here, both in the long term and the short term? So heart disease is fully preventable, 90% at least, and that's really reassuring. By heart disease, we mean heart attacks and strokes. Then the number one cause of death for most countries in the world. And the strokes and heart attacks have similar mechanisms of the arteries getting clogged up by various bad things going on, and we can see there's a similar pathology going on in both organs. So the slides are slightly twisted from my view, sorry about that, but I'll just walk through these from when I made them at home. This is just a quick plot of how the breakdown of the cause of death would look for the whole world. So a few years ago, most deaths in the world were caused by cardiovascular disease. Visually, it's massive, it's really, really big. Cancer's coming up, it's trying to be the new number one, but it's still number two. In Estonia, it's the same. If anything, it's worse. So we have more heart disease than for the world. So if you want to study heart disease and where it's at, then you should come to Estonia, because we've got a lot of it. And if we break down the same view into two halves, dark blue means we know which are the risk factors that can predict it and explain it causally. Light blue means we don't know what's causing it. It's a mystery disease, maybe some unknown genes or unknown behaviors that we haven't managed to code. Then heart disease is thankfully largely dark blue, 90% explainable. Small amounts still unexplainable. Maybe some mystery genes in the future will help us. For other diseases like cancers, we've got a lot more mystery to get to grips with in the epidemiology, but that's for a different day. So with heart disease, once we know what the risk factors are, let's have a quick look at what the top ones are. You probably have some of this from your basic read of the newspapers, but it's the usual big things like blood pressure, diet, body mass index. People are often surprised at how physical activity is actually quite low, about 10 times smaller than diet. So if you're interested in health, longevity, heart disease, even weight loss, then it's all about diet, diet, diet. Don't really think about exercise, to be honest. That's what the data tells us. This is quite a reputable source from the Lancet a few years ago, which some colleagues in Tartu were also involved with. So that's just a quick whistle-stop tour of the big risk factors, and we should use most of these when we create risk prediction algorithms, if we can, because they will help us make the algorithms more accurate. And we can try and tag to those risk factors, if they're causal, some interventions that can modify those risk factors. So obviously, if you've got high blood pressure, well, ideally, you should not have salt in your food, but if you're eating salty food, as most people do, eventually you move on to blood pressure medicines. With dietary risks that you want to kind of modify upstream, you should really think about eating less salt. I mentioned that already. Eating maybe more plants, less calorific food, etc. And towards LDL cholesterol levels, that can be very effectively lowered using statins, which is a comparatively safe and cheap drug and underused. And tobacco, a very addictive substance that fortunately can be easily helped with people who use the right amount of counselling and nicotine products. So those are some of the top buys that we have in public health services that we want people to use more of, and we want people to be aware of, and we want governments to fund, and we want people to advertise. Unfortunately, most of the places where this should be used are not used, so we need to get that out there. But that's just for a bit of background about why it's useful to predict heart disease. Because if I'm going to tell somebody that, hey, you're going to have a heart attack in 5 years, it will often increase their interest in taking up these interventions. And one thing that I'm particularly interested in is statin medications, because traditionally using drugs is a bit easier than using behavior change because it's more standardizable. There's an available army of doctors ready to prescribe, whereas for behavior change, it's a bit more difficult to deliver. So just some examples of how heart disease has already fallen by as much as 80%, can you believe, in some countries. So this is not a pessimistic story. Let's have a look at Finland. Back in 1972, they had a lot of heart disease, and by 40 years later, so there's a blue line here, which is the observed mortality, it has been brought down by 80%. So that's just amazing. It's a near eradication of the majority of the heart disease burden. And how did Finland achieve this massive reduction? It's mainly by reductions in Smoking, blood pressure, cholesterol, combined together, that explains most of it. Some of it is still unexplainable. Maybe they just got lucky. Excuse me. So just a really nice, optimistic story that if people, get their minds focused on it and work hard, they can reduce heart disease dramatically. Okay, so it's possible, and we can do it in different ways. And the other kind of mathematical interesting thing is when you go back to those risk factors, the green lines, you can actually eradicate all of heart disease, or 90% of it, by more than one way. You can focus on something that's very kind of behavior change, like olive oil and nuts and healthy diets, or you can give people's medicines. But you don't need to do both, because if you did both, you will like eradicate heart disease twice over. They're not additive parts. You can eradicate disease by more than one additive ways. So even by doing a little bit of activity on olive oil, a little bit on statins, you can actually get huge returns. And just some illustrations of olive oil, which is why I keep mentioning olive oil. A paper from the New England Journal of Medicine, actually a reprint from an older paper. This is the reprint in 2018. This is a randomized controlled trial, just as you would do for trials. So you give people blindedly 2 groups. Half of the group gets a control diet, which is a leaflet that just says, hey, try your best to eat a healthy diet. This is what it looks like. Good luck. Go. And we see that 5 years later, about, 6% of people, developed heart disease. Sorry, I think it's actually, I'm reading that correctly. And then the other intervention groups, there are actually 3 arms. So control group gets nothing. One of the randomized intervention groups gets free nuts in the post. I think it was about 30 grams every week, which they can just eat or throw away, give their cat, give their dog. Dogs die of nuts. But if humans eat nuts, then they have 30% less heart disease, and that's a whopping finding. And the third group was given free olive oil, not just a small amount, but a litre a week. So if you imagine you got a litre one week and a litre the next week, that's a lot of olive oil. I don't know what people do with the olive oil, but they somehow consume it for health benefit because they have 30% less heart disease. And that's quite a whopping finding from randomized trials, which we can now take to the real world. Quite costly, so it's not cost effective. The olive oil industry was one of the funders behind this study. And if we made a proposal to the Health Insurance Fund in Estonia, Haigekassa, they may say, sorry, we can't afford that much olive oil. Maybe we'll go for half a litre. But dietary interventions work. They reduce heart disease, and we should not shy away from them. Statins are another one that I'm interested in. This is a quite small text. I hope you can see what I can't see as well as you can. So let's start on the left-hand side. If you look at all the evidence for randomized controlled trials, if a trial has reduced people's cholesterol levels by 1 millimole per litre, then on average they get about a 20% reduction in heart disease. And that's big and that's good. If you reduce cholesterol by less than that, just by half an mmol, then you get half the effect. And if you give people enough statins to reduce their cholesterol by 1.5 degrees, you can reduce heart disease by 25%. So that's a nice dose-response linear relationship from about 30,000 people randomized to these studies. So really strong evidence from randomized trials that they really work to prevent heart disease. What's interesting is that that's the estimate of how much benefit you get. There's also estimates of how much harm you can generate. So on average, we take 100 people, start them on statins, you'll prevent about 5 heart attacks, and that's really good. But you also cause 1 case of diabetes, and that's really bad, because diabetes is a nasty disease. It can cause blindness, leg problems, kidney disease. So you don't really want to get diabetes unless you can avoid it and not do that. So the right-hand plot explains the breakdown by baseline. So this is the same plot, LDL cholesterol reduction. It's either 1, 1.5, or even 2, similar to this 1 and 1.5 here. And the benefits here are in an absolute scale now. So how many events of heart disease can this drug, once randomized, prevent? And here you have a really nice breakdown of the risk of heart disease at baseline before you get the drug. So in the back, you've got these dark grey columns of people that are like really, really close to having a heart attack. They're about a year or 2 away. They're going to get one very quickly. And the people at the very front of the pack, these are the young and fit people that really don't really need to worry and maybe shouldn't be taking statins in the first place. So the trick about risk prediction is if you can get this risk prediction algorithm right and stratify people in this axis as accurately as possible, you'll generate massive, massive benefits to the users at the back who, unfortunately, will still generate a baseline of some diabetes, because if all these people take statins, you'll generate like a sort of ceiling effect, like a swimming pool full of diabetes, uniformly and all weights and all sizes. But the benefits are going to be concentrated to the people that are high risk that you manage to predict and you manage to focus your drug to. Whereas if you're generating a lot of diabetes here and it's almost washed out by the benefits of heart disease, then there's not real much point. So this is why it's useful to predict heart disease, to get the best balance of benefits and side effects. Okay, let me just quickly keep my eye on time. Does anyone else have a timekeeping? Okay, cool. So my pet interest is more like some of the socioeconomic stuff, just because that's how I've found to be a kind of emotional and emotive driver of my interest. So I find this moves me and gets me going. Socioeconomic status can be measured in different ways. People's educational status at the start, then later on what job they have, how much money they earn, what they do with their money, whether they buy houses. You can ask people what they have. Different countries do it differently. In countries like Estonia, it seems to be that education is quite a stable measure of SES, socioeconomic status. Other countries use different metrics, but they're very, very powerful predictors of heart disease. They're really, really strong. They really predict well. This goes back to the 1960s, a paper in Science, where they looked in the US and saw how people who have college degrees have, about 30% less heart attacks than people who don't. And even if you look at deaths, you get a similar breakdown of about 30% less heart disease once you get a college degree. So we've known this for a long, long time, but we haven't really taken this niche social science learning and translated it into real clinical, practical medical tools, and that remains to be done. You can also measure socioeconomic status in different dimensions and states, like some work that we did a few years ago using cohorts across Eastern Europe, and we found that all of these risk factors individually, even in an additive model adjusted for each other, still end up predicting heart disease. So this is mutual adjustment, as well as adjusting for age, sex, blood pressure, cholesterol, smoking, everything that we know about heart disease. We put in the model, and we throw these new guys in, and we still get additive hazard ratio, sometimes quite large, sometimes 2.0, which is quite big in heart disease. So the bottom line is socioeconomic status, even though you can measure it with one core trait, you probably have a couple of traits that are all additively important, and you should try and get signals from all of them if you can. So, yeah, we seem to know that Eastern European countries have, about twice, if not more, rates of heart disease. That's a problem. But we get a sense that these socioeconomic predictors of heart disease are particularly strong in countries like Estonia. This goes back to a paper also in New England Journal of Medicine in 2008 with colleagues, Marla Leinsalu, who's in Tallinn. And this is a whopping difference. So broadly speaking, if you're a man with no college education or no university education, in Finland you might have twice the risk of heart disease. But when you come to countries like Estonia and elsewhere, it's about 3 or 4 times. So that's a whopping sort of interaction effect or a kind of additive effect of the context and this lack of degree and this socioeconomic status, which is really, really dangerous and powerful in Eastern Europe. Just a final quick slide, which is quite interesting that we found out in a paper looking at some genes as proxy trials. So people have always said, if you go to the skeptics, okay, so these things are associated, but what if they're not causal? What if lack of education is simply a marker that they've got some weak genes or something else going on in your life that you haven't measured, which is the confounder that's actually causing low education and low heart disease? So we did a study where we tried to mirror a randomized trial. If you imagine you randomize babies to get certain genes that push them to get more education, will they then 60 years later get less heart disease? And each of these dots is almost like one gene or one SNP that pushes a group of people to get more education. And we see that on average, if you get a SNP that pushes you to have more education, you also have less heart disease. And that was one of the first times that people have used genes as a proxy trial to study an upstream socioeconomic risk factor. So that was quite exciting. But that's kind of away from the story of risk prediction algorithms that I was trying to focus on. So let's bring us back to the issue of the day is when we add these predictors together into heart disease prediction algorithms, what can we do and how can we use them in the real world, in the real setting? So in this paper where we derived some risk prediction scores using data from Poland, Czech Republic, and Russia, we measured some of the performance metrics in the derivation or training data set. We then validated it in the Estonian biobank data set, completely different country, different data collection methods. We've got very similar results. In summary, this is an old-fashioned heart disease prediction score called SCORE, quite boring, but that's what they came up with. We recalibrated it so it's, aligned to the current rates of disease we see in these countries, and we then threw in 7 new predictors that were basically similar to the ones that you've been hearing about today. And we saw that adding these 7 new predictors in, I'll show you this screen, I think, raises the C statistic, which is similar to the area under the curve statistic, by 0.02 units, which from our perspective is kind of normal and average. You get a similar benefit if you throw in everything about genetics, you get a 0.02 effect. So that's quite big bang for buck if you just measure people's 7 questionnaire items and get quite a whopping increase in risk prediction accuracy. And the same was seen in the Estonian validation sample as well. So that you may know that AROC is a curvular measure, so any improvements anywhere are good. But in clinical terms, it's useful to categorize people as needing drugs or not needing drugs. And then you see whether that's useful or not in terms of what they end up getting 10 years later. So if you binarize the risk prediction accuracy question, I don't know whether you use net reclassification improvement metrics. Maybe not. So that's just a binary form of the same. But it only is interested in reclassification across the threshold. So if I'm earlier on in my study using an old metric like SCORE and categorizing people who are like either very, very low risk or slightly low risk, from a statin prescribing perspective, that's an irrelevant question because they're still super low risk. Reclassifying them, making the risk prediction accuracy better there is irrelevant. And if people are ultra high risk already, and I make that prediction slightly more accurate, again, no difference because I'm still going to give them statin drugs. What I'm interested in is the threshold of no drugs and yes drugs. And if people are falling the wrong side of this prediction, I'm measuring with the NRI statistic whether I can get my actual true cases who end up having heart attacks to be high risk and getting statins, and the low risk people to be on that side of the threshold. So medically, risk prediction is mainly interested in binary predictions because that's when we give advice and treatments. So the NRI means that 7% of people in the derivation data or 14% of people in the validation data were more accurately reclassified on one side of the decision threshold using our new metric with 7 new risk factors. And that was quite a big finding, and we saw again that all these risk factors we threw in were having additive effects. There wasn't a driving force by one predictor. They were all giving small signals, just as small genes would do in the same way. So a poly-socioeconomic risk score, if you will. Okay, so moving on to the interventions and how these work out in the real world. How much time do I have? 5. So when we look at what has been happening for decades in interventions that try to pick up people that are at risk of disease and give them something that helps them, we usually think about cancer screening pathways because the process of developing cancer screening pathways is very, very rigorous. It's very hard for a enthusiastic sort of tech entrepreneurial-minded person to say, hey, I've got a great idea about how to screen cancer better. Believe me, let's do this crazy new program and fund me and have this done forever. Because the cancer screening authorities are highly, highly suspicious and critical, and they want to see lots of steps and randomized trials before they will eventually enable a cancer screening program to be launched and funded. So they're very rigorous, and this is the usual process of how a screening service should be developed, but it isn't always how it's done in the real world. But ideally, you start with the whole population, you exclude those that already have disease, then you try and use any existing data that you have. So back in the day, you just take age and sex as your prior guess of disease, and then you exclude them, and then you move on to inviting everybody else to some simple tests. It might be an X-ray. These days we can talk about a phone SMS link that says, please complete a short survey with about 10 questions about what your self-reported behaviors are. And then for the small group of higher risk people, you invite them to something that's a bit more costly, maybe more invasive, like a biopsy procedure that can cause pain, bleeding, sometimes side effects. And eventually, for those that of the biopsy who you think are most likely to develop disease, even though some of them won't, you give them all some heavy treatment like surgery or drugs. And for the whole package of these steps, using A, B, C, D, and E, you really should combine that into a big package and randomize it in a country so that half the people get it, half of them then don't, and then you can see whether it actually works. Because it's one thing to theorize it and say this all sounds quite plausible, but it's very easy to generate lots of side effects, pain, anxiety, and problems in the process. So for example, with prostate cancer, there's lots of hype and belief that you can do helpful stuff, but if you end up poking lots of things into men's prostates, you can cause very severe side effects. In the end, that might not be worth doing if they would have died of these findings anyway that you thought were cancerous. So cancer screening is a fine art between getting the balance right of being too interventionist and doing nothing, and they've got a methodology which I like. I'm trying to now extend this to heart disease research and interventions. Maybe there's a battery going, potentially. But what's happening in cancer and what's happening in heart disease is that in the UK, they've taken the same approach to heart disease screening, but they've done it in a very quick way without having the proper rigorous steps, because some politicians thought it was a great idea they learned about in the States. So they came back with this health checks concept, and they're doing an offer to everybody who's aged 40 and above to have a heart disease-related health check, and they're invited to see their GP. Prior to that, one of the things we were working on is to make a prediction score. So we look at their healthcare records from the family doctor, and we see that by predicting who's going to have who's going to be in need of statins, these are the people that need statins, they actually clump quite closely to the right side of the spectrum. So we can identify them quite easily. And rather than inviting everybody for this health check, which is what the law says we should do, my proposal was to not give the service to half of the people who really don't need it. And the green people were, in one area, removed from this quite wasteful offer, and we only lost 1% of the benefits of these 1% of black dots being lost. And that was a really helpful cost-saving exercise, using a very helpful data trawl for an existing GP data set to say, hey, you're wasting a lot of money on this cohort of people who are green who don't need this service. The next step we did was to offer some of the lower risk, or the kind of yellow people in the middle, a digital self-assessment website, so they get an SMS. If they don't read the SMS, they get a letter in the post that says, hey, we sent you an SMS, what happened, can you not open it? You simple person, please download this system to use the QR code and go to our website and tell us what's happening with your heart disease. And we kind of developed this step by step, within a local authority. This wasn't like a high-tech company. This was just a couple of administrators and bureaucrats making this very quickly within a year or two. And in the end, we still see there are things that people often don't know. So they don't know what their blood pressure is, what their cholesterol is, but then we tell them where to go. So we will say, go to the pharmacy, there's a machine there, you can put your hand in the pod, it measures your blood pressure. People even test their cholesterol at home. We send the blood kits to their house. So we managed to make most of this service to take place before they go to their GP, to the family doctor, which is quite cool. And that's now happening on the ground in London, where I worked before. The whole point of this is to get the low-risk people to be stayed at home, reassured, and the high-risk people picked up and then sent straight to their GP to talk about statin drugs. But we do know that this service is increasing inequalities. This is just a breakdown of the uptake of this general service. By and large, if you happen to be black, Asian, or a minority ethnic group, there's about 60% smaller chance that you turn up, whereas white people use this service more. So generally speaking, these high-tech digital approaches are, loved by white, rich, affluent, well-educated people, and less used by those people that need it most, which is where this project comes in. In Estonia, we basically don't do any of this for heart disease. All you need is, if I knock on the GP's door and say, hey, I've got a problem with my knee, by the way, can you just do a quick check of my heart disease risk for the next 10 years? Maybe we'll use some algorithms together, and if I think my risk is high, can I please get some statins? They will give me a statin if I really ask them, but I have to be super informed and educated to make that offer, and most patients will never do that. So there's no system to invite people in Estonia, as most countries don't have. And it would be nice to have something, because it's the #1 killer. So in brief, my kind of hope is to kind of step by step get to this end game of having a system to roll out in a randomized way in Estonia, but we have to work up all these services first. It's going to take a bit of time, and the first thing we're working on, by the way, the randomized rollout doesn't always have to be in a big block, so you don't always have to go live with half of your GPs and half of them in the control arm. You can do it in a very comfortable step-by-step manner, and this is the stepped wedge randomized controlled trial design, which is just as rigorous as the regular design, but it's easier to implement for large places. So in this project, one of my final 2 slides, which we've recently got funding for, what we're hoping to do is get data for half of the residents in Estonia who happen to be aged 40 or above. Sorry, everybody in Estonia. So this is an N=all sample, because we think that having a smaller subset is not going to give us enough power. And then we're going to hopefully link to lots of rich data sets about their social states from these Estonian registries that are quite unique internationally, because we haven't really got other countries in the world that are quite as well lined up with social data readily available as we have. Link it all together to the health records, and then do some interesting methods. So this is just my back-of-the-envelope first stab of the methods. If anybody wants to help me improve these, join me, or trying different methods, then please do help me and join me, because right now the team is small. So yeah, we could do this in a classical parametric way, using just simple logistic regression, or we can do something more fancy and complex, compare the models head-to-head, etc., etc. The point is to squeeze what we can out of this data set and predict who's going to get a heart attack, and we're going to have about 5,000 events. There's plenty of data to play with. Yeah, I guess that's pretty much it for me. And the hope is not only just to create an interesting database to play with, a new medical device to predict heart disease. This should be one of the first medical devices that is purpose-built with the intention of narrowing social inequalities in health that are otherwise widening. So that would be an illustration of how we can generate new medical devices using available data sets in a socially sensitive manner that should be inequality sparing rather than widening. And that's what we hope to illustrate in this project today. Thank you. I think that's me.
Thank you very much. I think we have time for one quick question until our final speaker is ready. So, anyone? Yep.
Thanks. How many countries or individuals from different countries, do you have individuals from different countries included in this study, where you want to do the imputation, the problem that you just presented?
So this study should be only within Estonia, but if there are opportunities to expand and compare results from other countries, then we should try and explore what we can do internationally as well. But right now the proposal is just a within Estonia country study. But ideally, if you know of any teams that have similar data available, they will be quick to compare. That would be fantastic.
There are. We can take this offline. Yeah.
Great.
Okay, and thank you again. Now, our final speaker, please.
This is on now? Okay, so I have the fortunate slot of the day. I'm the last presentation. And I'm technical presentation, so to spice it up, I'll speak in German, because I heard a lot of German today. Probably not, but because I'll be terrible at that. So hello everybody, my name is Stefan. I'm from CSC in Finland. I'll be presenting a story today of my involvement developing standards and technologies for sensitive data archiving, mostly as part of the NAIC collaboration and as a lecturer. And hopefully you'll find something interesting. View this as my personal experience developing these standards, not as something that is the norm. And I'm fortunate to present the work of many, many people. This is what I'm presenting here is the work of many, many people across many, many years and many, many conversations and meetings. So I'll start with our researcher, which is at the focus of all this. Why we're building this, and we need to understand a bit the landscape, or I needed to understand a bit the landscape, why I was building this. And there are four main pieces that need to, or several, depending on how you view it, to share and reuse, to publish, to store and compute, and to have a control access of the data the researcher produces, uses, or at any point wants to share with other researchers to make it discoverable. Well, this is nice in practice, but there are several factors to this. How do you share and reuse? How do you publish and make your data discoverable? Most of the data is going to be sensitive in this particular aspect. Also, control access, because we're speaking about sensitive data. A data access committee needs to approve access to this data so that in a store and compute environment, other researchers or yourself, when your research collaborators, can compute and process it and store it for midterm or for even short term, or even to archive it in longer term. Moreover, after you compute and store it, you're producing new data, so you want to share that, make it publish it or discoverable, use some open standards to make it discoverable, have identifiers so you can use it in scientific publications. Because once I learned that identifiers are quite, dataset identifiers are quite crucial for researchers in their scientific publications, because they need to be issued by a known authority. And I recently learned that DOIs are not preferred by everybody. So yes, that was a shocker to me. So EGA identifiers, if you ever heard of European Genome Archive, some of those identifiers they're publishing in the bioinformatics field, they're really known, and they're preferred by certain publications. Now, a few principles to consider. These are not all the principles, just a few when we started working on all of this. Well, we need to have data at rest encryption. Why do we need this? Well, we're speaking about sensitive data. From a data processor standpoint, encrypting the data is really important. Moreover, we would also like to have this data re-encryption. Why would we like to have that? Well, when you are exposing data, it's nice because you're encrypting it with your own key or with your own password or something like this, but would you share that password with everybody or that key with everybody? No, you need to be able to encrypt it, and you need to be able to encrypt it fast, because that data is going to be used on the fly by certain algorithms, by certain software, and you need to be able to encrypt it quite fast and quite easily. Moreover, you need to somewhat educate researchers about encryption and data re-encryption, and that's a problem, because if you talk with them, nobody likes it, and it's an overhead about it. After all, and after that, you of course need to have the FAIR principles, because one needs to have them at some point, and to make it discoverable by other researchers. But we're speaking about sensitive data, so you cannot just say, does this data contain this person? No, you need to query it in an aggregated manner. Do you have in a data set something of this nature to make it discoverable by other researchers? And of course, it needs to be reusable. Yeah. And all of this needs to be under controlled access, because once you're archiving it for mid-storage, you cannot allow everybody to access that data. And you need to encode what that data can be used for. Is it general purpose research, or is it just for studying melanoma or a specific type of melanoma? I'm going to have an example about this. All this is all fun and games. Hopefully you run into some of these things. If not, yeah, there are certain standards to actually help with this. Some of these were mentioned by Abdulrahman, and there's a nice alliance, GA4GH. I'm not sure if anyone heard about it. It's Global Alliance for Genomics and Health. They're an authority which they're quite known in America, across the pond, and in Europe, in Elixir at least, in Elixir Europe. And there are certain standards. Most of them have heard about G4G passports. I'm going to point like this. Beacon maybe. Crypt4GH, I'm not sure how many heard about Crypt4GH, or and Duo, and HDSGet, RevGet, and Finopackets. Maybe Finopackets is well known. But I'm going to focus on certain standards today. Mainly, I'm going to focus on encryption standards. Hopefully, I'm not going to bore you with encryption, but I'm going to tell you why we use this specific type of encryption. And then I'm going to focus on Beacon, which is a discoverable, making data discoverable. Then on Duo, and I'm going to reiterate some parts of passports, hopefully quickly. So, what is encryption? What is this standard G4GH or Crypt4GH, or why is it important? Well, it looks like this. It has two main parts, which is the header part and the data part. The data is split into 64 kilobytes chunks. And why it is important and why it's different than other standards, AES or any kind of symmetric encryption, is because of this header. This header is important for us when the standard was designed, because it allows encryption with multiple keys, multiple recipients. What does actually mean is that I can encrypt the key, encrypt the file to be decrypted by only me and Abdulrahman. Not all algorithms can do this, if you can imagine. This is important. It's even more important, this encryption standard was designed in mind for genomic files, meaning you can specify in the headers means of accessing just specific portions of and decrypting just specific portions of a file. There's the data list header packets, which can specify getting just chromosome X from this and X position and dropping all the other packets which are not relevant to that sequence which you're decrypting. So this was really important for us, because we could, with that header, we can actually re-encrypt just the header and re-encrypt it for a different person. So we don't need to re-encrypt the whole file. If you have 10, 20 gigabytes, 100 gigabytes file, if you're getting like this, you don't need to re-encrypt the whole file, thus reducing the processing needed for encryption. So we can serve the file on demand by just splitting the header and the encrypted part and re-encrypting just the header. So this was important for us when we were designing and working with these kind of standards. Now, jumping a bit further to discovery, I mentioned Beacon. Beacon, well, we need to work on sensitive data. Well, and I meant aggregate data. So we need to query the data in such a manner that you don't actually understand, you don't actually reveal what's inside it and make the data, maybe you can hint what persons are during that data. So for example, Beacon was made for identifying variant calls. Not sure how many are familiar with that, and I surely cannot explain it. But it can answer questions such as, do you have C at chromosome 13 at position 32, 93, those positions? And it will answer with yes or no. And even more so, it has another level where you can specify if certain persons with certain levels of access can access that information or not. So it has a public, controlled, and register access, which you can make these kind of queries. This was Beacon v1. In Beacon v2, it has more information that is added, bigger standards that you can encode, facets it, you can explore the data, and so on and so forth. So it provides more functionality, and I'll leave it for you to find out more at this address. But if I'm going to leave you with one particular aspect, is that this beacon makes the data discoverable, but it doesn't point you to the data. But instead, with handovers, it points you how you can get access to the data, because you might need some sort of passport to get access to that data, or that data can be used only in specific instances. Which brings me to controlled access by this data use ontology. What's the data use ontology? Well, it's a means of encoding certain information when you're registering a data set in your system to specify what it can be used for. So let's say, for example, we have, pointers elude me today. We have these amount of studies, from study A to study G. Well, let's say a researcher would like to study melanoma. However, by data use restrictions, I think HMB stands for Health, Medical, and Biosciences, or Bioinformatics, or something like that. Or GRU stands for General Research Use, and data use uveal melanoma and cancer. So there's different data use restrictions that you can use from these codes from data use ontology. But a researcher wants to study melanoma, what he would have access to, what they would have access to. Well, they would have access to study C, E, A, B, G, but not to study F and D, because study F is a specific type of melanoma, but they want to study melanoma. And that specific type, they're not allowed under this data use specification. And with diabetes, of course, they cannot, because it's not there. This is a nice way of encoding. And there are systems that actually would read this kind of information, but data needs to be encoded somehow in your system. Then I'm going to briefly go over passports, because Abdulrahman already mentioned, but this is how the standard looks like. And the visa, what is encoded in a token that Abdulrahman mentioned, it looks like this. So this is how it looks like in the format, decoded, and you can encode different kind of information, so like affiliation role, if they accept the terms and policies, researcher status, if there's researcher by a valid university. So you can, if they don't have a researcher status, that maybe you don't want to exclude it, and controlled access grants and linked identities. The last part is important. The linked identities is important because there might be researchers from different institutions, or they have different, they might be affiliated to different institutions, and they have different emails. And you might want to specify that in your passports. And you can also build systems that issue these kinds of visas. We as CSC, we build a system that can actually issue these kind of visas, and a password broker can read them. A password broker being something like Life Science or Elixir AI, you can send that visa information to them, and they can put it to a passport clearinghouse, which can be a beacon in this case. That's why it's discovery there. And they can read that information if a user researcher has access to that or not. What's important here, and you might want to consider, is restricting what sources you trust for passport visas, because certain providers might be spoof and they might have the same data set identifiers, and you might run into trouble there. Now, about data archiving. In NAIC, from Trygve 1 to Trygve 2 to NAIC HELSA, we started building technologies for sensitive data archiving, and this is what it looks like. It's a microservice architecture with multiple services, and it takes into consideration many means of deploying this in different infrastructures. From Norway TSD, from Sweden in their own Bianca servers, to CSC infrastructure and ePOTA cloud system. What's important here, and I'll come back to the Crypt4GH standard, is that in this system, in order to add extra layers of security, we started separating when we ingest a file, we started verifying that the file we can decrypt, and after we decrypt it on the fly, so there's nothing stored anywhere intermediately, and we can quickly even detect if it's a file that we know and we can decrypt. We store the header, the encrypted part, and the key separately in the system. So they don't, very few services here, from Verify to maybe, I forgot which one. Verify, I think might be the only service that have access, and data out solution that have access to a key and all the pieces to reconstruct the information. So you minimize the attack surface area where an attacker could get access to the data and actually decrypt it and figure out what's inside. And if you want to get access to it, I mentioned a system which we built. You might know it as REMS. You might have heard of it, Resource Entitlements Management System, which is built by CSE, which can control access, issue visas, and get the data out of the system if the researcher or the other people have access to that data based on the passports. Now, how does this look in practice? And I'm not sure how I'm on time. 5 minutes? Okay, sorry if I'm over time. This looks in practice like this at CSE. So we're building sensitive data services, and we're thinking to making everything easy for the researcher. We're thinking this from a data processing standpoint. So for example, if a researcher wants to come with some data to us, they don't really need to care about encryption. But the data will be encrypted in our system because with the Crypt4GH standard, we are able to encrypt the data with our own plugin on the data on the user system, if they upload it to a browser, or they can be encrypted themselves and store it in our storage. And if they want to compute it, they'll have access in our own remote desktop environment. And if they want to publish it, they can publish it and attach metadata to it with this, and then specify what the user can access that metadata with data use ontology terms in our entitlement management system, which is REMS. This is all tied together. And if they want to get access to the data that has actually identifiers and metadata, they can apply, and a data access committee can get access to that data. They can approve access to that data, and they will be able to stream that data in a desktop. Why streaming is important for us, so we don't store the data with the desktop. We stream the data from a secure environment, from our archive, to this desktop, and we can, of course, re-encrypt it on the fly, and we're working on a system to re-encrypt the data with the user's public key, and they will be able to see it here and use it quite easily. So this is all I had, and some additional resources if you have some reading. These all libraries for Crypt4GH were developed, and they're being actually developed also in some tools. If you're familiar with bioinformatics, this is quite a standard tool. And all these from C, Rust, Go, and Python implementation were developed in the past 3 years for Crypt4GH, all by the team which we've been working with. Yeah. This is all I had to say.
Thank you very much. So I'm sure we would all now love to continue our discussion in our lovely cafe, where there is now a large selection of snacks and drinks. We can ask our presenters and other people what we've learned here today. Thank you very much to all our presenters. I have a bit of a gift for you from our institute to survive these dark Nordic evenings. So please, before you go to the cafe, please come to me. But again, thank you very much, and let's have a pleasant evening.